होल डेस्कटॉप नहीं किया मैंने शेयर, मैंने सिर्फ ये विंडो शेयर। So mic. Hello. How do we check it? Okay. Anybody on Zoom? Can you hear me? Yeah.
Yes, sir.
Okay, perfect. Thank you. Yeah. इस हॉल के लिए तो एक्चुअली माइक की जरूरत नहीं है, इट्स ओनली फॉर द जूम दैट यू
एक्सपेंड हुआ है तो इतने बड़े कोई नहीं है.
So
I'm doing the honor.
okay, you are in one of the new seats. Thank you.
Tired of sitting in this seat.
Hello. So this is another sound check. Can you hear me? Yeah.
Yes, we can.
Yeah.
That
Hello.
confirms that you are also online.
Yes. Okay. We can later as well. You don't have to wait that long.
Okay, good afternoon, everyone. Welcome to the weekly astrophysical seminar of Aries. And today we are very happy to have Professor Divya Oberoi with us from NCRA TIFR. Professor Divya Oberoi is a professor at NCRA TIFR. He did his PhD from IESC and TIFR in 2000. And then he moved to France and then later to US before, and then he finally came back to India. And he's an expert in solar and heliospheric physics. And today he will talk about recent advances in coronal physics from radio frequency observations. So Professor Divya Oberoi, please, the stage is all yours.
Thanks a lot, Vaibhav, and thanks for the nice introduction. Perfect. Thanks. Okay, so I gave a rather grand title to this talk, sort of recent advances. They are recent advances, but they are sort of limited to what I have been up to. So they are not, I'm not going to cover the whole area of solar and heliospheric physics. Okay, and before I start, let me acknowledge my collaborators. So all the names in different shades of red are students. The deeper shades are PhD students, present or past. So they've all contributed in many different ways to this body of work. Not all of it, of course, is being presented here. Okay, so because I felt that maybe there were not many people very familiar with radio observations of the sun in this audience, I thought I'll start by giving you a very quick introduction to what do you actually see in radio observations? What is the part of the sun which is emitting? What are the emission mechanisms, and what can you hope to learn from that? And that leads us to well, if this is what you want to learn, what should a telescope be like, right? And then I connect that to the telescope I'm working with and the work which we have been doing recently, right? And at the end, I have some remarks for hopes, aspirations for the future. So informal seminar, we have a small audience. Please feel free to ask any questions whenever you feel like. Answers are not always guaranteed, but I'll give you my honest attempt. Okay, so we're all taught that the sun is a black body like all stars, and that is what you see here, right? So, sorry, I went.
Yes, sir, pointing backward. Sorry, forward button.
Yeah. Okay, I was expecting a different. Yeah, don't worry about it. Right, so this is the regime where the sun is our brightest, 5,800 Kelvin. This is the regime where most of you are used to studying the sun, right? Somewhere maybe from here to higher energy or smaller wavelength side, right? EUV, X-rays, and so on and so forth. And I look at the sun way down in the other regime. And if you just pay attention to some numbers here, the peak of the solar spectrum is 10 to the power 8 in these limits. At about 1 meter, it drops to 10 to the power minus 16, right? So now that's whatever, 24 orders of magnitude drop. So now you would wonder, why should anybody study the sun in the part of the spectrum where it is giving out practically nothing in terms of energy, right? So the answer to that is what I'm trying to show in this particular plot, where, so these parallel lines are just sort of Rayleigh's laws corresponding to different temperatures. This is supposed to be 10 to the power 15. And what you notice in this sort of cartoon spectrum of the sun is that as you go to these lower frequencies or longer wavelengths, the spectrum of the sun begins to deviate from this 5,800 Kelvin. And by the time you're at about a wavelength of a meter or so, it is closer to 1,000,000 Kelvin in terms of a black body temperature, as opposed to the 6,000 you were expecting. And that is just a quiet sun. If you were to think about the active sun, its spectrum actually, I should call it spectrum. This is really an envelope of the peak of the emissions which you see, and it actually rises beyond 10 to the power 12 to something like 10 to the power 13. So if I was more careful, I would have drawn it something like that, right? So there is something which is giving out extremely bright emission at these radio frequencies, and that is what you can learn about from these radio studies, which is actually absolutely invisible when you're looking at the optical or higher energies. Okay? You already have a clue to the fact that what might be giving out this emission, because this is rising to 1,000,000 Kelvin.
It's coming from the distance.
Yes, so that's exactly what I'm talking about next. This is 1,000,000 Kelvin. What else do you know around the sun, which is 1,000,000 Kelvin, right? The coronal. So all of this emission is actually coming from the coronal. So at about these frequencies, you barely see the photosphere or the chromosphere. It's at a temperature of 10,000 Kelvin. Right? It is contributing, but a lot of that emission is being absorbed by the overlying corona. And even though the corona is not optically thick, it has an optical depth getting close to unity, but an optically thick is infinite optical depth. Right? So the contribution of that million Kelvin corona, despite its sort of lower optical depth, outweighs or outshines that from the chromosphere or photosphere by a huge amount, right? And that is what we are studying. So what are the various emission mechanisms involved? We're just talking about the corona, and at the center here is the free emission, right? This is electrons being scattered off other electrons or ions which are available in the medium. So this is the free emission. This is proportional to, as you would guess, the electron density which is there. It also carries a dependence inverse to T to the power 3/4. Right? These are the two things which it really depends on. L is some mean free path. Another frequency which we want to keep in mind is the so-called plasma frequency, because this decides what wavelengths can propagate and which will get absorbed. Right? All frequencies shorter, or sort of all wavelengths longer than that corresponding to plasma wavelength will get absorbed. Right? And only higher frequencies can propagate. And that is what is sort of a graphical view of these is what is shown here. X-axis is frequency, y-axis is the height in solar surface, above the solar surface. And this nu p is our plasma frequency. And you notice that in around this region, right, nu p and nu tau are close to each other. And that tells you that a lot of the thermal emission which is going to happen here, you are going to be able to see. And these are all average numbers, right? So in reality, things can bounce up and down beyond that. And the other thing which I should, where do I need to point? Here. Okay, the other thing I should have pointed out is also this gyro frequency, which is naturally proportional to the magnetic field, which tells you that one of the things which you can do at these radio observations is to also have a direct estimate of the magnetic field. So that is really applicable only at much higher frequencies as compared to what I will be talking about. Okay, never mind. Okay. So, like I said, thermal free emission, it will tell you about the large scale electron density and temperature distribution. Right? And because it has a certain dependence on electron density, and we know that the coronal electron density falls very steeply. Right? This means that you can use this essentially as a probe of different heights in the coronal region. So that is what I'm trying to show here next. So there are two consequences of that electron density gradient, this really massive electron density gradient. One is that if you were to just take any coronal model, and this is cycle model, which I'm using here, and trace the rays, just follow Snell's law in the corona, you will end up with something like this. Right? So these rays are not going to propagate all the way to the sun. There will be some distance of closest approach beyond which they will turn. And that is the distance at which this ray is going to encounter its highest electron density. So the measurement which you make is going to be dominated by the radiation which is arising at this surface of closest approach. Therefore, by sort of dialing my frequency back and forth, I can peel this onion. I can make myself sensitive to different layers in the corona. And that is what I mean by peeling the layers of this onion. And it is really quite hard to get this information because I can go up to somewhere, let's say from 1.2 solar radii to something like 2 solar radii or even beyond in the region where I'm able to do this work, where I'm able to get a handle on the large scale electron density and temperature, which as we know is very hard to get at higher energies. Okay. The other thing which we can do is the following, that this radiation, when it is born in the solar corona, it's unpolarized, it's thermal, free emission. But because it is propagating through a birefringent medium, the refractive indices for the X mode and the O mode are slightly different, which gives rise to a net circular polarization. The circular polarization is low, but it depends on the magnetic field, which is there in the medium. So if you can measure that really low circular polarization, you can also get a handle on the ambient magnetic field, ambient large scale magnetic field, which again is very hard to do by any other means. Okay, so that was about the thermal part of the emission. There is also the non-thermal emission, which comes, let's say in this slide, I've chosen to divide it into two classes, incoherent and coherent. So for the incoherent class, primarily it is the gyrosynchrotron emission. And this is the gyrosynchrotron emission, which comes from essentially the CME plasma, the plasma of the coronal mass ejections, which we know has energetic electrons and magnetic field, which are the two requirements for your gyrosynchrotron. And there, essentially, if you are able to measure the brightness temperature, that gives you information about the electron density, actually not just the electron density, the spectrum of energetic electrons, the thermal electrons which are present, the temperature of these electrons, and the magnetic field. So that's as much as what you can learn. And there's a whole class of coherent emission mechanisms, usually referred to as plasma emission. These are all resonant phenomena, which means that they must be narrowband, and also they tend to be directional. Right? So these are coherent emissions. Narrowband, they take place typically, not typically, at the fundamental or the harmonic of the local plasma frequency. There again, if you can measure the brightness temperatures, that is related to the rate of growth of the instability. That again is an interesting thing to be able to measure. And they have a whole range of, and there's a zoo of these things, which is something
So
I showed.
when you say instability, it is the instability of what?
So these plasma emissions are typically caused by some instability or the other. The most common one is because of, so some magnetic reconnection has taken place, which has energized some bunch of electrons. These electrons get organized into a beam because of overlying magnetic fields. So as this sort of suprathermal electron beam is propagating through a thermal plasma, it is giving rise to instabilities. So that it is setting up Langmuir waves, and those Langmuir waves are decaying via these electromagnetic radiation. And that is what you can measure.
So these are transients, right?
These are all transients. Yeah. Okay. So there's quite a variety of these things. So this axis has time on the x-axis and sort of frequency at which you observe the phenomena on the y-axis. So I'm not going to talk about all of them, but all I want you to notice is that they can vary from things which sweep very rapidly across frequency, known as type 3 bursts. There are things which sort of stay put over the same place and frequency and can keep happening for a long time. Right? This cartoon is just sort of earmarking or trying to show you how would this emission look in the frequency time frame. Right? So these are all very different characteristic shapes. Okay. And these type 3s are something which we will come to a little bit later as well. Then in terms of polarimetry, the solar radio emission also offers a huge variety in terms of the degree of polarization of this emission. So this far axis, vertical axis, it shows the degree of circular polarization. And this one shows the brightness temperature. There's also a huge range of brightness temperatures involved. Right? Brightness temperature, I assume, is a concept you are sort of familiar with, because the radiation which you are receiving from something, if it was coming from a black body, what would be the temperature of that black body? That is simply the brightness temperature. So it can go up to as high as 10 to the power 15 in terms of brightness temperatures. On the lower end, it could come as low as something like 10 to the power 5, and or actually 10 to the power 4 if you're looking at the gyrosynchrotron emission. In terms of degree of circular polarization, it is anywhere from close to 0 or less than 1% to close to 100%. Right. So this is the object we are trying to study. It's something which is giving out emission at okay. Okay, I'll come back to what I started to say just after this slide, maybe. There's one more thing which we have to be aware of, which is that on its way from the corona to us, this radiation gets modified because of its propagation through this coronal medium. Right? As all of you know, the corona is not a smoothly varying medium. It has this large 1 upon whatever r to the power 6 sort of density gradient. On top of that, it also has a lot of inhomogeneities which are superposed. Right? So because of that, there is a lot of scattering. And remember that this radiation is at a frequency close to the plasma frequency or its harmonic. So it is going to see a lot of propagation effects. It is going to see a lot of scattering, absorption, refraction, and so on. So this cartoon shows essentially if you were to release a delta function of radiation at this point, what would be its propagation like? So there is just one impulse which was released there. And this is what it would look like if you were to go with the typical expectation for what the density inhomogeneity distribution should be like in the coronal medium. And what this is showing you that if I choose a surface, say somewhere here, and I just want to see the size of that delta function, right? It's really a pinpoint from where the radiation is coming. its size grows as a function of time because it takes rays which have been scattered more a little bit longer to arrive to your vantage point. So you can see this growth in size. And this is just a distribution as a function of time of the radiation which is arriving. Right? So what started out as a delta function has actually spread out to have this sort of a distribution. Right? And you would expect the unscattered ray to come around here. There is practically nothing which is unscattered. Right? Most of it has been scattered somewhere by a small amount or a larger amount.
Yeah, so I have a question. So these coronal inhomogeneities, you mean to say density, temperature, or magnetic inhomogeneities, or everything?
So what matters to the electromagnetic wave is primarily density. Right? But what has given rise to this includes the magnetic field as well. And
Generation.
yeah. So all of so I didn't talk about that. These guys are already talking about an isotropic density inhomogeneity distribution. And that has certain consequences as opposed to assuming purely an isotropic density inhomogeneity. So these are, because it is plasma, it is easier for it to be elongated along the magnetic field than perpendicular to that. So that is the reason for those inhomogeneities. So magnetic field has an effect, but not a direct one.
I mean, they themselves are responsible for the inhomogeneity density as well.
Correct. Yeah.
I mean, from these radio observation, can one measure the
Density
size of
inhomogeneity.
density inhomogeneities? I mean, because
So
Fluctuations, yeah.
it is possible under certain situations to do that. We have tried to do that. So you can find out, are we, for example, in the weak scattering regime or in the strong scattering regime? If you can measure this growth in this size, that tells you what sort of a scattering medium you must have come from. So those sorts of things it is possible to do, and we have done some of that. I will talk about it.
So there will be strong polarization evolution also along the time.
Completely agree.
This is what will give rise to.
So there will be a strong polarization.
So the
evolution.
temporal changes in the
changes in the polarization.
Yes. So
will
I
be
will,
good sort of-
Constant on that.
yeah. Good diagnostics that way.
correct. Yeah. So that is something which we have just started to work on. I'll tell you where we are with that. It's very hard to measure. That's why it's not been done till now. But I'm glad that you picked that up because that is something we are also very excited about. Okay, and so how have we been learning about the sun thus far? A lot of what we know, and we know quite a lot, has come from non-mathematical. In the I think somebody has already. So a lot of what we know has come from non-imaging observations. So what can you learn from that? Just like I was showing you that dynamic spectrum, right? The shapes of various things. That is essentially what you can learn, and it's quite amazing actually. What all can you learn from that without making any images, without knowing what does it look like, without knowing where it is on the sun? You can still learn a lot, mainly because those events are few and far apart, right? If a type 3 is happening or some other type 2 is happening or something, they happen so infrequently that when a CME is happening, you know that this is coming because of that. And you know this emission must be arriving close to the shock front because that is where my theory says that this emission must take place. Right? So that is why we are able to go a long way without even imaging. There's also another thing with these radio guys that there is no obvious counterpart in other wavelengths. Why? Because all of this emission is coming from the coronal. Most of the wavelengths are probing your photosphere and chromosphere and maybe transition region. We are sitting well above that. So you can trace what you're seeing to something else which has happened at lower heights, but you won't see a counterpart. Right? Unless you might see a counterpart sometimes, very few times, in terms of say a gyrosynchrotron source sitting on top of a cylinder. That again I'll show examples of. And of course, you are limited to comparatively stronger things because your antennas are typically going to have a very wide field of view. So what you are receiving must dominate the galactic background and the quiet. Right? Okay. There have been, of course, a whole lot of imaging instruments which have been there. I'm just listing some of them here, and these are some of the newer ones, which at low frequencies, which I'm particularly interested in. All of my work comes from this particular instrument, the Murchison Widefield Array, 80 to 300 megahertz, located in Western Australia. So just to remind you, what is the object? What is the sort of object which we are studying, or what are the characteristics of radiation from this star? Temporal variability, which can vary over scales from solar cycles to milliseconds. Spectral variability, like I showed you in this particular figure, it could get down to 100 kilohertz. And the smooth spectrum, the black bodies, or not the million Kelvin black body spectrum, is of course pretty smooth. Brightness temperature ranges from 10 to the power 4 to 10 to the power 13 or 15, depending on which theory you believe. 13 has been observed, 15 has been predicted, not yet observed. Degree of polarization, all the way from less than 1% to 100%. Spatial changes in morphology of the emission over very short time scales, right? So this is the object which you want to study. So now you want a telescope which should be able to capture all of these. So that's a really tall order. And that has been the major reason why solar radio astronomy has not managed to become mainstream. So I'll make it a little bit later. So this is just a pretty picture of the telescope which I use. It has 128 such tiles distributed in a very barren landscape, population density of few millihumans per square kilometer. Among the most, least hospitable places to live in. Temperatures in the shade can exceed 50 degrees centigrade routinely during the summer. So your equipment also has to survive that temperature. Right? A very small footprint. Then first built it was around 3 kilometers. Now we have a smaller configuration and a larger configuration. So depending on how you configure it, between 2 and 5 kilometers, 128 such guys. Half a second time resolution, which has now improved to actually quarter second, and 40 kilohertz resolution, which has improved to 10 kilohertz now. Okay. Now,
So just there's no protection around there.
Is the protection you need really is only from kangaroos here. There are no humans there. So what has happened over the years? So earlier we used to find that some cables are really tangled up, and that our theory was that there were these wild animals which were running around and therefore got caught in these cables, and that is what led to them. And they're very strong, but these antennas, they have very sharp edges, which have not been ground on purpose just to deter any of these animals from coming close to them. So after that, what we started.
There's a grid in the picture.
This is 5 centimeter by 5 centimeter
So
grid.
their legs will get trapped probably.
No, but kangaroo have a wide.
Yeah, they have a hoof which is probably not get trapped, and the kangaroos and their emus. They're both very inquisitive. They're not used to humans. They're not used to having strange things appear in their surroundings. But this has been there since 2013 is when we formally started to observe. So by now they sort of let us be and we let them be. But we had to go through a phase where we had to sort of roll all our cables into a single thick thing, buried shallow, so that it doesn't catch anybody's foot when they are.
So I have a question. I mean, I don't know much about radio telescope. So is there a requirement like optical telescope for site survey, or you can install it in the backyard or anywhere?
There are, the reason why we went to this least hospitable place is because we want to move away from radio frequency interference. Right? So that is a key requirement. And that essentially these days means go to a sparsely populated area. The other requirements are you want to go to a place where the ionosphere is not very active. So this is mid-ionospheric latitude. So that means the ionospheric disturbances and the ionospheric dynamics is quite low. The third thing you might say is that, well, I want to access as large a part of the sky as possible, so I don't want to go too far away from the equator. That doesn't work for us because close to the equator, the ionosphere is very active. So this is at -26.
Yeah, Ladakh would be.
Ladakh would be great, but we also want a comparatively flat place. So the gradient over, so I did the site survey for this telescope. The gradient over 3 kilometers is 3 meters. What they call a river, you will drive through and you will not even realize it's a river, because it gets water only when it rains, because there's a very shallow gradient, the water flows there, the mud doesn't absorb the water, it stays there till it evaporates. So it's a sort of strange place. So I'm running slow, but I don't necessarily have to get to the end of my talk. Okay, you stop whenever. I know that there is something else we need to celebrate a bit later. Okay, so here is an example of a dynamic spectrum from the sun, right? You can see on the x-axis time, on the y-axis, these are sort of the speed chunks. Okay, the reason I put them up like this is I want you to notice that in the quiet sun, there is a lot of structure in this emission. These emissions are not strong by the standards which I was showing you earlier, those type 1 through type 5. These variations would be invisible to most of our existing telescopes. These are really small, but they are there. They are very small in short-lived in time, right? It's here. This total time is 5 minutes, time resolution is half a second. So it comes and goes very quickly. It's very narrow band. So that tells you that no thermal emission can produce it. It has to come from a non-thermal source because it has a sharply peaked spectrum and it comes and goes. This was really our first clue to start to look for something related to really weak flares from here.
Is it the entire is for the white sun, or also I mean, this part is
in these 5 minutes there is no active sun. If you looked at, I don't have the date and time here, but if you looked at, let's say, activity reports from any telescope across the world, nothing was reported, even in preceding hours or later hours.
there are two, I don't know, one is 239.
Yeah,
That region the intensity is pretty high. So,
correct. So 239, 270, these guys tend to be higher. Then there are occasionally something here which has come and gone. Right. You're absolutely right.
why is that? Why is that close to 300?
So it will not always sit here. If I choose a different day and a different time, it will not look. These guys would not always seem most prominent. It's going to shift. And that we think is because all of this are really very weak magnetic reconnections which are taking place, which are giving up sort of puffs of energy all over the place. Now, that emission is being generated at the fundamental or the harmonic. Depending on the height at which those activities are taking place, the frequency will shift around. So that is what is our.
But the duration is also much longer.
Their duration can be, so different kinds of emissions are there. Some of them.
So this strip is basically time 5 minutes you have said.
Right.
So there is some mixture with the thermal. It can be.
So there is a lot of thermal.
Yeah.
Thermal million Kelvin is sitting there. On top of that,
Yes.
these are the fluctuations.
So here what I'm saying is, since you are giving this scenario of the reconnection thing, that has of course multiple things. It does accelerate the particles. It also heats the local environment as well.
Yes.
So these could be also signature of both.
These could be signature of both, but here the local heating, the volume which is going to be there is really tiny as
Resolution,
compared to
yes.
the rest of the solid. And this is actually not from an image. This is just one baseline. So I'm looking at the whole sun, inside the entire sun. So I'm not resolving anything out.
So
I
that
don't
is
think-
unlike.
So that is not going to produce much. Now
If you always forget about this radio resolution versus our
right, yeah. You find it very hard to fit the sun in your field of view, right? And we see practically the whole sky in our field of view, and the sun is a tiny part. So the nice thing about MWA is that for each of the pixels on this plot, I can make an image. So I can see how this thing, if I have an image, I can see exactly where is this coming from. Is it happening at the same place again and again? Right? Where is it? How is it moving in time? Whatever is happening, I can figure out. But if I really wanted to do that, I'll end up making 500,000 images every 5 minutes. Now, that's, impossible really. I don't know if any of you have radio imaging experience. It's intrinsically a very iterative process, computationally very demanding. So it's really not feasible to do it. And fortunately, because I don't really have to, because most things seem to have a bandwidth of at least order a megahertz also on this. So I don't have to really make an image every 40 kilohertz. I can sample it more closely and still get most of what I want. Okay, so apart from maybe what I showed you in the last slide, none of what I told you was unknown prior to MWA, right? But what changed with the MWA was the following. So the radio interferometry is essentially a Fourier imaging device, Fourier imaging technique. Each of your baselines is measuring one Fourier component. The larger is the number of these guys which you can measure, the better your inversion is going. Because my things are changing very quickly and over short bandwidths, I must get my data also over short time spans and short spectral spans. Right? That shoots the technique which radio interferometry typically uses, which is time synthesis and frequency synthesis. So now the only way to do it is by having a large number of individual elements, so that all your baselines sample your UV space or sample your Fourier space densely, which is what this instrument managed to achieve for the first time. This red circle is supposed to bar the Nyquist sampling rate for a 1 degree sized object in the sky. Okay, so if you have done, if your sampling is of this order, then nothing can escape your Fourier decomposition. You still need to have sensitivity and so on. And this is the first telescope in the world which has managed to do something close to this. Right? And usually it doesn't matter because most radio sources can be described like a bunch of Gaussians. You don't really need Nyquist sampling. But here we get pretty close to that. The other thing which you need to do is you need to build the ability to do a lot of imaging reliably and without human intervention. And that has been a large effort on our part, and we now have state-of-the-art imaging pipelines. So here's an example from the first one of them. Right. So this one, the dynamic range here, right? That's the ratio of the peak to the faintest or to the noise in the image. Right. That exceeds 10 to the power 5. That's sort of unheard of in solar radio astronomy otherwise. This is for the case of a bright type 2 burst. That's the most convenient time to do something like this. You can still see the faint sun, even in the presence of this very bright emission. This is at 10 to the power 9 Kelvin, okay, the brightest peak. The sun is about 10 to the power 3 or 10 to the power 6 Kelvin, billion Kelvin. The image on the right is for a quiet sun. Right? You see that this is 10 to the power 5 here. So this is sort of 5 orders of magnitude fainter than what this guy was. Both of these have come from the same pipeline without human intervention. The range of variability or the range in brightness distribution which you see on the surface there is very low. Right? That is your sort of big featureless disk. That is the thing which is hardest to image when you have a featureless large blob. This one, yeah. That marks the resolution of our instrument. Yeah. That is what he was referring to earlier. As compared to you guys, we are essentially blind. We can't make out anything from the image. Okay. So the key takeaways are essentially that we do have a robust pipeline capable of working in an unsupervised manner. 2 to 3 orders of improvement in dynamic range, and we really represent the state of the art. And naturally, if you are making a jump of 2 to 3 orders of magnitude in anything, you will find a host of new things. Right? That's some of what I'm going to talk about. This is the next sort of incarnation of that pipeline, which now also does polarimetry. So this is just some examples, and this only last month it got published. So these are some of the well-known type solar bursts. So type 1, the images on the top are circular polarization. So this guy shows something like a peak of close to -60. That's another one which shows a peak of around -25% polarized. This is linear polarization, which is I'll talk a little bit more about it, actually maybe a fair bit more about it as we go on. And this is the quiet sun. I was mentioning earlier that if you can measure the very weak circular polarization on the quiet sun, it gives you a way of estimating the ambient magnetic field. And this is, we can get to something like 0.2% uncertainty in this region and around 0.7% uncertainty in the outer edges of that. And this is, I think, we're still working on it, but I think we're close to making a reliable measurement of this low level of circularly polarized light from the quiet sun.
So did you involve these and estimated magnetic field also?
Not yet. We are still working on making the radio measurement a little
So
more
these
detailed.
contours, so there's a focused region. So can it be mapped with some active region location?
In this case, yes. Yes. So I should have said that the contours are Stokes I, and the colors are, so Stokes I is total intensity, and Stokes V is the circular polarization. That is what the colors show. Okay. So what we managed to,
So that's a very powerful probe. And
yes,
in principle, if you have a very good calibration, you can get an estimate for the field as well.
that's exactly what we want to do. Right? So we just want to gain a little more confidence in this measurement. And then we want to go after that inversion. That inversion is fairly well prescribed. But I think it's a paper by C.H.V. Shastri, which was not first, but which last talked about it. I think there was a Nature paper in 1970s which first talked about that.
And I think it's a good thing because keeping in mind that Aditya is launching and then we have the spectro-polarimetry in Aditya itself. So probably at some point of time we can have like coordinated observations with what you guys are doing and what we can do, and then a cross check how good it is.
Yeah, right. Or as you will be measuring it in the photosphere.
Yeah, okay. But this is
No, it's the Coronal.
it's
in the Coronal.
in the Coronal, yeah. So then we
So
can.
we will be at around 1.3 to 1.4.
Yeah, yeah, so we are
So it's
1.3.
basically, it's difficult to go up to 1.3, but around
But if there is
1.1, 1.2.
but if there's a prominence eruption and
Huh,
associated
Yes,
CID,
yes.
then
If there is a
we-
structure, then we
that's
will.
what I'm saying.
Otherwise,
That would be fantastic.
yeah.
Yes. So you would be doing it on the limb though.
Yes, yes.
We would be doing it
On the disk
Yeah.
mostly. So actually, since you mentioned this connectivity of any structure
Yeah.
to the like if there is a prominence,
Right.
which is at the anchored somewhere. The problem is at the limb, the magnetogram things are not very reliable in any
Right,
case. So these combination could
Yes.
Would
be
be
that's
very
what I-
useful, yeah. Right. So I think, yeah, we are, I think, close to unlocking that. We are really excited about that. This is part of thesis of this guy. So it's certainly going to happen in the next year. Then Jyoti is there, becomes connected. Okay, so I will not insist on going through everything which I have, but I'll give you some examples of what we have done. So the first one is what we sort of playfully named as wings. So these are weak, impulsive, narrowband, quiet sun emissions. These we think could potentially be related to coronal heating. I'll tell you a little bit more about that. There's these polyperiodic pulsations, which we have been finding in all sorts of active emissions, which we have been looking at. We have detected Gaussian neutron emission from CMEs. For every CME we look at, we have found it. The rest, maybe I'll not talk about. Coronal heating, I don't need to say anything about that to this audience. So I'll just say that, well, people have put in a lot of effort in looking at power laws of these, weaker and weaker flares, and we believe we can go down to nano-flare energies now, but we are still sitting at minus 1.8 in terms of the power loss load. And those who have looked at spatial distribution, they find that the spatial distribution of these flares sort of mimics that of the spatial distribution of active regions. So we know that it is not going to be your solution to coronal heating because even the polar colonize. So we need to look for something else. And that's where radio sort of comes in, because wherever you are doing reconnection, there is no way but for you to accelerate electrons. Whenever you are doing that, you are, and there is going to be an overlying magnetic field because that is what has reconnected to give rise to this. You are going to form these electron beams. These electron beams are going to set up that bump on the tail instability, which is going to radiate via this coherent plasma emission. Now, the key operative word there is coherent, because this is a coherent class of emission, like a laser. It is going to produce a much larger observational signature as compared to the thermal signature, which we have been looking for in X-rays and EV. So that is why I wanted to do this. Right? This was already there in the 2004 science case, which we wrote for NCRA. The reason why it is hard and nobody has ever wanted to do this is because it's very impulsive. So you think it will come and go in less than a second. It's very narrow band, right? Or now we know it's order 100 kilohertz. And these are going to be, despite their coherent nature, these are still going to be very weak. This is milli SFU. One SFU is 10 to the power 4 jam speed. For those of you who are familiar with jam speed. Solar flux units is what solar radio guys like to measure the flux of the sun. Okay. Around 100 megahertz, the flux of the sun is about 1 to 3 solar flux units. Okay. So this is 0.1% roughly of that. That's a very hard measurement to make. Okay. So we were very excited when in 2020, a couple of years ago, as a part of Shivaji model's thesis, we discovered what we eventually gave the name of wings. What we are looking at here is a histogram of essentially this one. So this I is about index associated with one particular region, T is over time. This is the mean. Okay. So I take the time series, I subtract the mean from that, or the median actually of the mean, and divide it by the median. So I'm left with essentially the variable part of that. Fractional variability is what you are seeing. Now, if all of this was thermal, there is no reason for you to see a power law in that. So that is what got us excited. That look, there is in this fractional variability which we are seeing here, there is this power law. And in terms of SFU, so this is now sort of this was actually unitless in some sense. It was a ratio. In terms of SFU, we are sitting between 1 and 10 milli SFU. That is where I actually took the number from what I gave you earlier. And it took a lot of effort to do this. Some 33,000 images needed to be made to get there. So that tells you that the pipeline was essential to be able to do something like this.
Yeah, so again, I mean, since you are using SFU as the unit, so I mean, if we convert these energetic events in terms of, let's say, Earths, where would they fall? In microflares or nano-flares or picoflares, where do they fall?
So that's certainly that from a coronal heating perspective, that is the question you want to ask. There are two problems here. The problem is that this estimate is of a coherent emission. Now, going from that coherent emission to the energy which would have been deposited in the plasma requires you to make various assumptions. And we can, of course, make those assumptions. If you were to do that, you would land up in
Picoflares.
That's correct.
And there's another thing here. So, like the power law index is greater than 2 here.
Power law index, yeah. So it is greater than 2,
Yeah.
which is a nice thing.
Yeah.
But which says that, yeah, this could be
Coronal heating candidates.
but what we have found is that this is very variable. Right? Here already you can see from 3.5, 2.16, 3.7. Right? Different data sets don't always have the same. And the even more surprising thing was that in this particular data, there was this big active region sitting there, which we said we will ignore. Actually, this is not a big active region. This is a small active region, but it appears very bright in the area. So we said, okay, there might be contamination from this guy. We are going to ignore this. We did various tests. The emission coming from here, does it seem to be correlated with anybody else? And wherever the correlation was even 0.6, we said we are not going to use it. Okay. Despite all of that, we found that when we go to an extremely quiet sun, what we see, that distribution, that thing which had the power law value in the same quantity, now begins to look something different. Not only that, this guy stops at 0.2. Previously, if you notice, this was going up to something like, say, 1. Right? So the funny thing was that the brighter guys have disappeared. How should that happen? But between that work and this work, we had improved our technique, we had improved our images. There is no way the brighter guys can disappear. And so we dug into that and found that all of the, if you look at the distribution of the brighter guys, they are all in the periphery of that active region. And if you look at the sort of annular bins, the larger is your annulus, the smaller is the number of those brighter guys. So we think these were actually all coming from there. But now we don't see a power law here. So that sort of reminded us of a paper by Polon and Solanki from a long time ago, where they had tried to, I think I have mentioned here, no, sorry, wrong button, where they had tried to model the the time series. They had sort of sampled it using the expected sampling function of an UV instrument, and ended up with this. So this is what, if you were to fit a log normal to this, that is what this thing would begin to look like. So that is again very exciting. I don't remember clearly. I think it was not EIT, I think it was something else, but we can check that out. So again, that was really exciting. So we have no doubt that these guys are good. We have to understand better why their distribution is whatever it is. Of course, we have been doing now a lot more work about understanding these things, whatever you could do from a radio image. So we are now looking to see what do they look like in the image plane. Like earlier work was blind, like you just take a spot and look at the time series and look for outliers essentially. Now, if you take an image of the sun, these are, for example, what these wings are looking like. This guy is showing you their spatial distribution all over the sun. This is a 40-minute sun. So you can see that they are happening everywhere. They're not confined to just the equatorial belt or where active regions are or anything like that. And these are again, you can see a normal function appear in their distributions. The orange ones are the ones which we are able to fit well with the Gaussian. The blue ones are all the ones which we detect. The ones you are able to fit with Gaussians, you can look at their area, intensity, axial ratio, and so on. So all of them look essentially compact. They seem to make sense to be what a small reconnection event might give rise to. You also tried to look for EUV counterparts of winds. Now, individual wind is really too weak to be able to look for their counterpart. But we found in our data some places where there's a bunch of them which are happening at the same place. And there, if we try to look for that, so here, the blue solid curve is radio. The dotted curves, dashed curves are different AIA filters. And we found, this was work by Shurajit model, we found two locations at the radio contour where this was happening.
I think, I mean, just came to my mind. Recently, Solar Orbiter has launched EUV, and then there are a lot of like campfires which have been discovered. So probably we can write some sort of proposal to have joint observation, and if these peak things are related to those.
You're absolutely right. So you probably
PI is a good friend of ours, so we can actually.
So we can have
PI, Solar Orbiter, it's in the ROB, and some nice line group is there involved.
because you're using SDO and these events, but you have enclosed in square, right? These, so these are something which is very similar to the campfires that.
I completely agree with you. So one of my former students, Rohit Sharma, he's like him, right? So he's now with the FH and W group. So he's working with Sam here. So So we have put in a proposal for that.
Okay. So they are part of this.
Right. Okay. So that you're absolutely right. That's something which we would also like to follow up. But to our surprise, it so happened that these were the two potential candidates, and the one whose time profile matches the radio is this guy, not this guy. So the one who's sort of, there's some 6 arc minutes or so difference between these guys. So it's not particularly close. And if you were to, so now that you have detected it in EUV, now you can do your DEM and get a sense for what it is. And that comes to 25 or so. But this was a collection of things, not an individual thing. So the general idea basically is that, well, the radio source which you are looking at was born around here. These electron beams are sufficiently weak that they get dissipated very quickly, and their timescale matches that of electron collision timescale. So that is essentially what we are saying, that it's not just that reconnections are happening close to the surface, they're happening everywhere. Because if I'm seeing it at these frequencies, these beams could not have propagated from somewhere far away. It must be born somewhere in that vicinity.
Yeah, these events actually, our prediction was long back that it is all happening in transition region mostly.
Okay.
And Sumer spectrographs also identified by specific spectral lines.
Okay.
Explosive events. So they are basically all linked.
Yes, right here. Yeah, so these guys are about 25. So again, brings you, but this is a group, so brings you into nano-flares sort of region. This is actually work by Rohit, which is under review right now. So we want, because this can potentially have significant implications, we wanted to sort of dot all our I's and cross all our T's. So we wanted to detect this using a different technique as well. So this is something called residual visibility. Basically, you say that, okay, I'm going to look at only median subtracted visibilities from every baseline which I have and try to make images of that. And there only the time variable things should live, right? Everything else should go away. And that is what we try to do here. These are examples of the images which you get. The red, blue, green contours are the sort of 5 sigma contours on the boundary of the sun. And the bright things which you have popping out are these rings. There again is a distribution of where are they on the surface of the sun and how many of them are there. So goes all the way from 108 to 240 megahertz. That's the sort of range which we are able to cover with the MWA. You can also look at how bright these are. This is brightness temperature in kilokelvin minutes. Okay. So something maybe 4 or 6 kilokelvin is their brightness, which is there for the peak guys. Right? So there's some you can see also transitions happening as a function of frequency. Right? You can see sort of continuity between different frames as you go. So these are clearly associated with some other phenomena which is happening here. But all this sort of yellowish stuff which is covering the entire disk, that is clearly something which is happening all over the place, as you would expect something within that. Okay, so where are we now? We have detected it in multiple different data sets, including some very quiet conditions. There are tens of thousands of them per hour. So again, you need an automated technique to do that. I didn't mention it, but the place where we were looking at the morphologies, that comes from an AI ML pipeline. To do that, we see them to be distributed all over the sun. Their morphologies are Gaussian, bandwidths are over 100 kilohertz. So far, we have not found anything to say that these could not be the counterparts of nano-flares. Right? So we continue to push that. What do we want to do next? We want to look at polarization properties, temporal structures, and also perhaps do some simulations to find out that if this is what I finally want to see in radio, what does it take to produce that? Right? That's sort of outside our regime a little bit, but some work on that has started. Okay. How much time do I have? So
So what I suggest is, in principle, if you are coming back, from the last part, we can have a smaller group discussion because there are plenty of more material.
Right.
Some of the students will be probably benefited. We'll work it out.
We can
so
do
this
that.
formal seminar we can.
Yeah. So what I will do is I'll talk about this because there is some question about polarization and what you might learn from that and propagation effects and so on. So this is a so-called type 3 burst. This is a group of type 3 bursts. Each of these vertical stripes is one type 3 burst. This is Stokes I, total intensity. This is Stokes Q percentage.
It's look like a simulation better than. Yes, so
this is very high signal.
Yeah.
Okay. So now the big issue in radio observations when you're doing polarimetry is leakage. Right? How reliable is your measurement? Because you have these two orthogonally polarized feeds which are sitting right next to each other. And any current which is introduced in one is also going to produce a radiation which is going to couple with the other. Right? So that is the hardest thing to do. That is why it has not been done well so far. That's what we've been working very hard to get a handle on. So but any leakage which is taking place should not vary over short temporal and spectral scale. Right? So if I look at it as a percentage of Stokes I, it should essentially be constant. That is what is being shown. This is Stokes Q percentage. So you can see that it is varying quite dramatically. It is not identical in structure to this, but typically wherever you have structures in there, many of these places tend to have structures in Stokes. Right? So this gives you a reason to believe that whatever is you are seeing here, it is the property of the incident radiation which is changing. It is not coming from my instrument or my analysis. So we think it is really true linear polarization. We can make an image like I told you, right? So this is the Stokes I image, and this is the Stokes. This is not the linear polarization. We're calling it P, which is sort of Q squared plus U squared under root. Now, what was one source here breaks down into two polarized sources with their polarization angles which are changing, right? Okay, so again, no leakage is going to give rise to something like that. A leakage from Stokes I would be a scaled copy of this image by definition. Right? It is some fraction of that has leaked into this. So it's going to be a scaled copy. This is clearly known. You can, in fact, see the fractional linear polarization for the same image as before. If I plot the fractional linear polarization, I see change across that source. Right? So all these things are pretty firm evidence to say that we have really detected linear polarization from these type 3 bursts. So why is this surprising? This is surprising. Okay. Something I skipped over earlier. According to the theory of type 3 bursts, you expect 100% circularly polarized and no linearly polarized. The conventional wisdom in solar radio physics has been that there is so much differential Faraday rotation going on in the coronal that all linear polarization at low radio frequencies should be white. Some of it we are able to overcome because we are looking at 40 kilohertz spectral channels. Earlier, people have looked at megahertz wide spectral channels. Right? So certainly, we are looking at smaller than an order of magnitude spectral band, where naturally this would be much less. And people had never managed to beat down the leakage to the level which we are able to do. We have really excellent models for the telescope and good, much better calibration algorithms than have been available in the past. So we really believe that we are managing to do that. This is more detailed. So something which might interest you, if you look at the area of different sources, blue is I, red is linear polarization, and green is Stokes. The sizes of these sources are also different. I'm not showing it here, but their positions are also moving with respect to each other. And you expect the circularly polarized source, okay, scattering is supposed to lead to loss of polarization. And my most polarized sources or polarized sources are always smaller than the Stokes. That is giving me some indication that as scattering is happening, that there is some scattering which is happening. My polarized sources are always smaller. Sure, I'm including it. Okay. Not sure if your eye will pick out here, but there is an anti-correlation between this, the linear circular polarization and the circular polarization. If you look at the cross correlation, you see it different. This has a lot of white because of an issue with our pipeline. So all of that we will be able to fill. That pipeline failed because of various reasons and this different frequencies. But we have good data. We'll be able to fill it. This is just where we have reached. So this is sort of telling you that there is an interplay between Stokes V and linear polarization. Like our conventional picture of Faraday rotation is that if this was my sort of Poincaré sphere, right, or this was my, say, Q axis, U axis, and V axis. So V is my circular polarization. Whenever my Faraday rotation is taking place, it is around the V axis, right? So my degree of linear polarization is always conserved. But if you have a more general model for the medium in which propagation is taking place, this vector along which this rotation can take place is actually along the wave mode of your propagating vector. So that can be at any arbitrary angle, depending on the nature of medium you are looking at. And there you can have, if my plane of rotation or if my axis of rotation is not aligned with you, then I can have a mixing of linear and circularly polarized light. And that is something which we are beginning to explore now, and that will be part of the thesis work of this guy, Soham Day. So I think that is probably, okay, I'll skip over this as well. I think the most important thing to say is probably this and the next slide. What we are looking to do, what we aspire to do, is to be able to measure the Faraday rotation because of CME plasma as the CME is traversing in the open space, right? 0.3, 0.4 solar radii, somewhere like that. This is the first image where this red circle is the sun used to be there, it has been subtracted out. You can see more than 80 background sources. This is like seeing stars in the day. Right? In presence of the sun, we are able to see these sources. The sun is tens of thousands of Jansky. These sources are all few Jansky. To be able to detect them with good signal to noise is something we have clearly demonstrated. Next thing for us to demonstrate is actually to also measure the polarization. That's harder. There are various complications, but we are working on it. That's where we want to go. So our idea is essentially a CME has been shot off. There are going to be a lot of background sources. If I have many lines of sight through that CME for each of which I measure the Faraday rotation, I'm eventually going to fit some sort of a flux slope model that has ordered 10 degrees of freedom. I give you 50 constraints. Right? I will have coronograph images, hopefully full videospheric viewer images. So with those data and the constraints which we bring to bear on the problem, we should be able to constrain the vector magnetic field of the problem of this scene. That is the holy grail of space weather. That is what our ultimate objective is. That's where we want to go. This is again about propagation effects. Okay, so once I want you to take away that what we are trying to do is to make solar radio astronomy more mainstream. It has not happened till now, mainly because there are very few telescopes which are dedicated to observing the sun. Right? The general purpose telescopes, it's very hard to find time to observe the sun. They're also not very well designed for the sun. And that has led to very few practitioners of solar radio astronomy. Right? And that also means that because we don't have a big community effort to build our pipelines and so on, it's very hard for new people to come in because there's a steep learning curve. You have to figure out from scratch how to deal with data from this instrument, that instrument, and so on. None of these reasons are intrinsic to the richness of solar radio science. These are all sort of technological, social kind of reasons. Okay. These are reasons which we can overcome. These are not reasons coming from physics. These are just how we have been doing our stuff. Okay. That is what we want to change. We have now a bunch of new instruments, which are not solar dedicated instruments, but they're pretty good for observing the sun. We can do fantastic science with these guys. The data they produce or the capabilities of these instruments are very well matched to what is needed for solar science. You can always do better, but these are pretty good. These are the best we have ever had. We have, of course, like we've been talking up, upcoming missions like Auditorium, which generate, just like we've been seeing, these additional synergies, curiosities, reasons for us to work together. Right? Cross-fertilization is always good. We are building a robust pipeline, which we want to sort of make available to the community. There's 3 petabytes of NWA data alone, solar data, which is sitting. Right? I have analyzed, which is more than 3,000 hours. I have analyzed maybe 3 hours of data with all my students.
Is that data public?
It has an 18-month, 12-month proprietary period. The rest of it is public. If you want to work with us, just write to me. We'll be very happy to work. We are drowning in data. We have more projects than what I can do in my lifetime.
So how does it take observations? Like, I mean, it's a proposal based or it's a proposal? It's a proposal.
So if you have ideas about something you want to propose, you can get in touch. I can share what we are trying to do. We have a fantastic track record. Since 2013, every observing semester, we've been getting 100 hours or so for NWA data. And so we want to make it mainstream because it's going to take us some time because I'm only working with students and I have a small number of students. And the student has to focus not on a sort of, production quality pipeline, but on his thesis, his or her thesis. But that is with our intent. This is what we want to do, and this is what we want to make public, so that it does not require you to be a black belt radio astronomer to make good radio images. Okay? That's what we are aiming for. So with that, I think I'll just leave the summary up here. Thanks for your patience and questions are welcome here.
Okay, thank you, Divya, for giving a very nice overview of solar, the radio observations from sun. So, any questions we can take? Yeah, please go ahead.
Yeah. So when the talk was going on, I thought of asking linear polarization already. So we're very close to doing RM synthesis.
We will be, so that will be our next step. Once we are able to, so we sort of take baby steps. So that
the path is there.
Path is there. Correct. So we have a very good instrument in that sense because we can spread our bandwidth across the 80 to 300 megahertz band. So that is what you need, a large.
The fractional bandwidth to the actual frequency is more than 1 kilometer.
Yes. So we are very well placed to be able to do that. So that is exactly, it is on our path. We have not reached there.
Has anybody done or probably not?
On the sun, I am not aware of. I don't think we need to.
I have a second short question.
Sure.
Other technique which we when you said this polarization is low frequency, classically, of course, pulsar machines were there and they were doing very different but similar, like detecting the burst. Now, of course, all these telescopes have an onboard transient detection. The data cannot be saved. So, any burst on the sun are detected accidentally or routinely in those data boards?
So, I think the answer to that is probably no, because all of so for example, for the MW, nobody else observes during the day. While the sun is above the horizon, they don't want to observe because their side lobes are so high, side lobes at NW are so high that even if the sun is above the horizon, its contamination is very strong. So they don't want to observe when the sun is up.
So the LOFAR is doing that.
LOFAR is doing so at NW. Some people have just started to do that. They take care to put the sun in a night of the beam when they are doing it. I know of one instance where a solar burst reflected from the moon has been detected by NW. These guys are very good. For wings, we are at the edge of our sensitivity. There we are going down to really SFUs. But for large bursts, we don't have.
Your answer is can be detected but not done.
It can be detected.
Within the reach of brains today.
I would say so. I think it is not done because people are expecting that and are avoiding the observing slots where it can happen.
Okay, any other question?
So, the way you started the talk, I just got a feeling that you were interested in to find out small irregularities of in the corona, which probably is the connection, small irregularities. Where have you reached with your results? What do you conclude?
So we find we have
And why is it important? You have a magnetic field, lots of things, right?
Right. So in the solar physics community, the coronal heating problem has been one of the longest time problems. Right? We all agree that you have to extract the energy from the magnetic field. And there are two sort of well-known ways of doing it. You can do wave heating, right? You can set up waves in the magnetic field, get them to dissipate, heat your corona that way, or you can extract energy via reconnection. So people have been looking at both of them. People looking at the nano-flare sort of scenarios have not found the flares which could be responsible for coronal heating. We have evidence for impulsive radio emissions, which we have no way of creating, or at least we have no known way of creating apart from these nano-flares, which meet all the requirements of these radio counterparts of these nano-flares. So that is where we have reached. We are trying to do their observational characterization to find out what their distributions are like, what their shapes are like. So there is another project which we have just started, which will look at sort of now you have a 4-dimensional space, right? Where is it happening, and time and frequency? Are there any structures in that space? So that is something we are just beginning to look at. That's where we are. We are also looking at higher time resolution data using the pulsar machine sort of data. We are getting close to the edge of the sensitivity of this instrument. Fortunately, MWA will be updated over the next few years. We'll have twice as much collecting area. That will help.
Okay, any other question? Yeah, online participants, do you have any questions? Seems like not. So I have one, probably last question before the. Okay, so you said that I mean you were looking those wings and then you were trying to find some observational signature in EUVs. So I just wanted to know, are there any such studies where, or what is the current status of the standard flare model that we have, where we have like radio emissions, X-ray emissions, and now we know that from there is a satellite known as the New Star, and from there we also have seen the gamma ray emission, or let's say hard X-ray emissions. I would rather say that. So if we do a multi-wavelength study, let us say, including your radio emissions, what you have shown here, then is it possible to let us say quantify or this standard flare model? Has someone done it already, or where we are in that?
So there are some people who have been working on it. So Ben Chen and his group of collaborators, right, from NCRA. So a lot of work on that has been done using the Oberoi radio telescope and some using the VLA. Now, for the standard flare model which you are talking about, what you are interested in essentially is what is happening close to the site of that reflection, right? So the frequency ranges which I was talking about are not very useful for that because we are sitting much above that. So there you have to go to sort of gigahertz and band, gigahertz or so kind of frequencies. And the Owens Valley telescope and VLA are good, are well suited for that. Owens Valley has an issue that it does not have that good imaging. But if you're looking for a bright point source, that is not a problem. That is what they have been doing. They have shown quite clearly that they can trace radio emission from right above the X point, and they can see it travel, and they can see it drop in frequency as it goes further. So there's a science paper I think from 2018, if I'm not mistaken. Bin Chen as the first author, which was one of the first papers to do it. After that, he has 2 or 3 more papers that show the same. That has been fairly nicely substantiated. We are not very good. This frequency range is not very good for that. So, okay.
Okay, if there are no further questions, let us thank Divya again. And we hope to host you again.
I'll be happy to be there. Thank you so much. Thanks, everyone. Thanks.
Durgesh is coming next week in person. Please.
Just unshare and log off from what I mean, he will end the meeting on his own. Share.
I'm already here. The Bindu first, second D. Yeah, the following before.